Alright, get ready for today's video on 7.4 inverse functions. We're going to start off with a word problem. Your mother is on vacation in Italy. Lucky, lucky her. You want to call her, but you know that international calls are extremely expensive. You have Verizon and they charge $1.50 per minute per international call. Fill in the table and plot your points. So if it's $1.50 per minute and we're on the phone for 2 minutes, 2 times 150, that means it's going to be a $3 call. If I'm on the phone for 4 minutes, 4 times 150, $6. 5 times 150, $7.50. 6 times 150, $9. We're going to go ahead and plot these points on our graph we've got here. So the x's and the y. So for 2 minutes, it's going to cost $3. For 4 minutes, it's going to cost $6. And for 5 minutes, $7.50. Kind of guesstimate there. And for 6 minutes, it's going to cost $9. Now I want you to use a straight edge to connect these points. I'm not going to be able to do that, so I'm just going to kind of do my best to draw my line through. There we go. But you know, you guys have your ID, which works really, really well for a straight edge. So that line is going to represent the number of minutes. It's going to determine how much it's going to cost. We're going to look at this data in a little bit different of a light. We're going to use the data in the table to show the relationship between the cost and the number of minutes. Plot these points on the same graph. So all we're going to do is take that list from above. So instead of having minutes on the x-axis, we're going to have minutes on the y. And we said that for 2 minutes it was going to cost $3. For 4 minutes it was going to cost $6. For 5, $7.50. And for 6 minutes it's going to cost $9. So all we did was switch our x and y values. Let's go ahead and plot these new points now. So this is now our x and this is now our y. So we've got 3, 2, 6, 4, 7.5, 5, and 9, 6. Again, we're going to connect these points, and your graph should look a lot better than mine. I'm not able to use a straight edge. You can use a straight edge so that you have nice, clean lines. Alright. This is going to give us the inverse relation. To find an inverse relation, all you have to do is switch the x and y coordinates, and that's what we did comparing the number of minutes determining the cost and the cost determining the number of minutes. All we do is switch our independent and dependent variables, or our x and our y variables. The graph of the inverse relation is the reflection of the graph of the original relation over the line y equals x. So it's really that easy in the fact of if I have a relation, which we are given in the first part, the inverse relation is simply found by switching the x and y coordinates. So all the x's now become the y's, all the y's become the x's. The first line we plotted was the original relation, so that's our f of x. The second one that we plotted with those switched x and y values is the inverse relationship, and that notation looks like that. Now the graph, in this case we just took our relationship and we flipped our x and y, so we had the points that we could plot. If we didn't want to do that, it is the reflection over the line y equals x. Y equals x is a linear equation. Y-intercept of 0, slope of 1. And we can do that in both directions. And when we connect that line, the original function and the inverse are just reflections over that line. So if I took the blue line and reflected it over y equals x, we end up with the green line. So that's our inverse relation and our inverse graph. Go ahead and turn on over to the back page. Now we are going to find the inverse equation. We found the inverse relation. Again, a relation is just the table of values switching your x and y values. Now I'm going to give you an equation and I want you to find the inverse equation. This only takes 2 steps. Just like the relation, first step is going to switch x and y. So we look at number 1, we've got f of x is equal to 2x plus 3. Technically there is no y, but we do know that f of x is the same thing as y. So this equation is y equals 2x plus 3. So step 1, we're going to switch those x and y's. So that's now x equals 2y plus 3. And our second step is to solve for y. So if I want to solve for y, I want to isolate y. First step is to move that 3 over. So we've got x minus 3 is equal to 2y. We're multiplying by 2, so we divide by 2. We get y equals 1x divided by 2 is 1/2 x minus 3/2. And if you remember from the front page, our inverse notation is going to look like that. It has -1 first superscript there. For number 2, same 2 steps regardless of the kind of equation you have. So this is really representing y equals x to the third. Step 1 is switch that x and y, so x equals y to the third. If I want to get y by itself, I'm raising it to the third power. So to undo that, I take the cube root of each side. So now y is equal to the cube root of x, rewriting it into the inverse function notation. And that's all there is to it. Number 3, again, switch the x and the y. So this is now x equals 3y squared plus 7. We want to solve for y, so we move the 7 over. X minus 7 equals 3y squared. We divide by 3. So now we've got y squared equals 1/3 x minus 7/3. We have y squared. To undo squaring, we take the square root. And now we have y equals plus or minus 1/3 x minus 7/3. Now all the rules of every kind of solving that we've ever had, we want to make sure that we're pulling that knowledge. We are solving for something that is being squared. Anything that we are solving to the even power, 2, 4, 6, 8, 10, it's always going to be a plus or a minus because if you have an even exponent, the negative would have canceled out. If it's being raised to the odd power, 3, 5, 7, 9, if the answer is positive, the x is positive. If the answer is negative, the original answer is negative. So we have y equals, oops, we forgot function notation. Oops. So that's going to be f to the -1 first equals square root of plus or minus 1/3 x minus 7/3. And I've got good news for you. When you have something messy like this, and it's these multiple pieces, the adding, subtracting inside, you do not have to worry about rationalizing. You can go ahead and leave that as your answer. Don't say I never gave you anything. Alright, number 4, again, first thing, switch out that x and y. So we've got x equals the square root of 2y plus 7 minus 4. We want to solve for that y, so we move the 4 over by adding that to both sides. Now we have the square root. We want to undo that so that we can get to the y. The opposite of taking the square root is squaring both sides. We do not have a plus or minus here. It's only if we were squaring, not if we were square rooting, because that square root has to yield a positive answer. So we square both sides. This is a binomial squared, so we've got to make sure that we FOIL that quantity to give us x squared plus 8x plus 16 equals 2y plus 7. We move that 7 over. So now we've got x squared plus 8x plus 9 equals 2y, and we divide by 2. So we've got y equals 1/2 x squared plus 4x plus 9/2. we change that into our function notation for our inverse. And we are done. So writing the inverse equation is simply switch the x and y and then solve for y. We've got one more topic for today, and that is determining whether or not f of x and g of x, if two different equations, are in fact inverses of each other. So if I give you two equations, instead of telling you to find the inverse, I'm going to say, are they actually inverses? To do that, you need to pull back from those composite functions from 7.3 and determine, is f of g of x and g of f of x, if they both equal x, then yes, they are inverses. So let's go ahead and start by finding f of g of x. And in case you forgot, this means I'm taking the g of x function and I'm plugging it into f of x. My f of x is 5x minus 2, but I'm going to take out that x and I'm going to put that whole g of x in for x. That's what I mean by taking g of x and plugging it into f of x. So this is 5. Every time we substitute, we use those parentheses. So we replace the x with x plus 2 over 5 minus 2. That 5 and that 5 cancel, leaving us with x plus 2 minus 2. 2 minus 2, we've got x. So we've got the first step, f of g of x is equaling x. In order for them to be inverses, both of them must be x. If one of them is and the other one's not, it's not going to cut it. We got to make sure that both of them are. So now we're going to check our g of f of x. We're going to plug our f of x into the g function. Our g function is x plus 2 over 5. That x is coming out and the f of x is going in. Our f of x is 5x minus 2. That's representing that whole x. Plus 2 all over 5. Now those parentheses don't really mean anything. They're just separating the two pieces. So we're going to add like terms. A negative 2 and a positive 2 leaves us with 5x over 5. And that equals x. So this means that yes, they are inverses because the f of g of x and the g of f of x both equal x. Alright, now I want you to try the second one on your own, and this is your last problem. So go ahead and press pause. Alright, let's see how you did. First, we find f of g of x, so our g of x is going into the f of x. We are substituting, so that entire g of x function gets put in parentheses. We distribute our negative 3. A negative times a negative gives us a positive 1x. Negative 3 times 2 is a negative 6. Add our like terms, and we're left with just x. G of f of x, we plug that entire f of x in, making sure that we have parentheses, so we distribute, and that gives us a positive x minus 2 plus 2, negative 2, positive 2, cancel, so we are left with just one positive x. Remember, if they don't both equal x, then they are not inverses. Anytime you are asked to verify or show that things are inverses, you must show the f of g of x and the g of f of x, and you must show all of your steps. You can't just say yes or no. You have to justify your yes or no answer. Alright, and that's it for today.